Okay, good morning. Let's get started. Sorry for the delay. So, as usual, please scan this one. This we need to check whether this one I need to log in here. Oh, this one doesn't work. So you need that add in, but so I will use my computer.
But this part is not working yet.
This part is not working. Okay, let me use my computer for that.
So this slide is linked with some software from your computer.
For this, you need a add-on. Add. I'll use my laptop.
For that,
Yeah, for that. Yeah, it's okay. We'll do that tomorrow.
tomorrow we'll
Yeah.
So in the last of the session we'll discuss with them and we'll fix in this
Yeah,
computer.
yeah. How to write on the board?
I think प्रेस करके डायरेक्टली देख सकते हैं इसमें वो
Okay.
right then you just have to
Yeah,
click
okay.
on this pen and erase it both of them.
Okay, good morning again. So, the part on material science is pending, but it need not be sequential. I will teach that portion some other time. Let us get started with magnetism today. So far I notice 29 of you have joined the book club. First question, like how did you come across magnets at first? Is there any way to switch between two screens? Switch between two screens. Because the answers will be here, they cannot see.
Okay, so for that sir, I think
First we need to connect here. And do you have any switch?
for here sir, for switching between
Yeah,
two
switching between the two screens.
I think so these settings need to be changed and this
Mm-hmm.
we'll ask them. सर का जो ये क्वेश्चन है उसका टाइमर और आंसर यहाँ पे दिख रहा है स्क्रीन में सर जब भी क्वेश्चंस के सेक्शन में जाएंगे तब तो ये स्क्रीन पे स्विच करना है और जब नॉर्मल पीपीटी में ये स्क्रीन पे पढ़ेंगे
Is it possible to switch between two screens? No, we need to connect HDMI. No switch, is it? Yeah. ठीक है, I think that's good. Yeah, we can do that. Yeah. I mean, those audience cannot see, but at least here they can see.
ठीक है, अब कैसे कनेक्ट
नहीं, एक काम करते हैं उसमें कनेक्ट कर देते हैं, जब वो ऑनलाइन आपका ये आना है तब वो रिवर्स करने से हो जाएगा। इस तरह मतलब थोड़ा लंबा केबल
हाँ तो उसमें कनेक्ट कर देना। वो तो मैं अपना वो लैपटॉप से कंट्रोल कर सकता हूँ ना। हाँ कर सकता हूँ।
लैपटॉप तो मैंने तुम्हारे जेती है ये तो डिस्प्ले को तो ड्रॉ करना है ना।
खुली यार लगा दीजिए।
Yeah, we don't need that display here. Yeah. So if there is any question, you just read to me. Okay, thank you. Okay, so many of you have said the fridge magnets, toys, broken speaker, inside the speaker, loudspeaker, all those things. Okay, that's so basically you get fascinated with the magnets because when you see magnets they attract something and they repel each other, and this is the property that as a child basically attracts people towards magnets. Okay. So, this property of attraction or repulsion comes from the fact that magnets produce a magnetic field. Okay. So, as you know, field is something that can produce force without contact. So, if you hit a tennis ball with a racket, there is a contact force, because of that contact force the ball moves. Okay. On the other hand, you keep a charge in the electric field, the charge will be attracted even without a contact. If you have magnet and if you keep a magnet, I mean iron, piece of iron next to a magnet, magnet can still attract, there is a force without contact, and that is what we call as field. So, magnets generate magnetic field, and this magnetic field can be used for many different purposes. Okay. For example, as many of you have written, fridge magnets is used to attract the magnetic material, and magnets can produce a force. So, you know that in motor we have magnets and we use a combination of electric current and the magnetic field to produce rotational motion, and the magnets can also be used for levitation. There are maglev trains. So, in China they have trains that go from Shanghai airport to the city at speeds of 400 kilometer per hour, okay, without friction, because it is a levitated train. So, this is also possible because of a magnetic field, and you also know that we can generate electricity from time varying magnetic field. So, if you look at the old bicycles, there will be a dynamo. So, there will be something that will be touching the tire. So, when the tire rotates, the dynamo rotates. Dynamo basically has a magnet and the magnet rotates. So, when there is a time varying magnetic flux as a function of when there is a time varying magnetic flux in the presence of a coil, you can generate electricity, and this is the principle we use in dynamos and transformers. And we can magnetize magnets in one direction or the other. So, you can keep the north pole up, south pole down, or south pole up, north pole down. You can magnetize material in different direction, and you can use this magnetic field to sense information, and this is what is carried out in magnetic recording. And you can also sense the magnetic field to know the bits. So, in magnetic recording, magnets generate magnetic field, and we sense that magnetic field to read the information, and we use compass for navigation and so on. Okay. So, with magnetic field we can do so many things. So, that is one reason why magnets are interesting. Okay. It goes to okay, that brings us to the next question. So, I talked about navigation. So, there is a question about navigation in your book lab. It's okay. It's okay. Okay, quite often, I mean, when I teach a class full of Chinese, they will choose Chinese. Okay. I don't know why you guys chose the Europeans, because Chinese is the first people to invent compass. Okay, the compass based on magnets was invented by Chinese. So, that is what many people will choose, and still all of you are wrong. All of you are wrong. The correct answer is others. Okay. So, my question is who. Okay. It does not mean only human. The first living beings used magnetic field for sensing, or actually bacteria and birds. So, you know that bacteria and birds evolved earlier than humans, and they have been using magnetic fields for navigation. So, Chinese invented only like 1000 years ago, but even before that bacteria and birds used magnetic field for navigation. Okay. So, now we have learnt about magnetic fields, how it can be used in various ways. So, now let us take a few steps to learn how we can generate a magnetic field. Okay. So, you know that you can generate a magnetic field by using a permanent magnet. Okay. So, if you have a magnet, you bring it near the fridge, it will stick, because that permanent magnet is generating a magnetic field. Oh, it is in the pen mode. Okay, so permanent magnet is one way to generate a magnetic field. Then you can also generate a magnetic field by using current carrying wires, solenoids or electromagnets. Okay. So, for example, you take a piece of wire, you apply an electric field, electrons flow, and as a result you will see that there is a magnetic field generated. So, magnetic field is produced when there is a motion of charges. So, electrons flow in a wire, produce a magnetic field. Okay, again another question, do you have any idea like when possibly this kind of phenomenon happen in the world? So, you know, one example is the Oersted, the scientist, he sent current through the ampere, I do not know who it is. So, he sent current through the wire, then he observed that magnetic field is produced, but is that the first occurrence of such magnetic field produced by a current carrying wire? No. Okay. For example, you take brain. So, in our brain we have neurons. So, neurons are connected to each other through something called axon. So, when we do any computation or something, there is a electrical current flowing from one neuron to the other neuron through axons. Okay. So, that current also produces a magnetic field. So, our brain, whenever brain operates, it produces certain magnetic field, and we can use this magnetic field to sense to understand the brain's working function. So, if you have heard about magnetic encephalography. So, in magnetic encephalography, we are sensing the magnetic field produced by the current flowing from one neuron to the other neuron. So, that produces tiny magnetic field, like very low magnetic field, 10 power minus 15 Tesla, that kind of very low magnetic field is produced by our brain. So, these are examples of flowing charges producing a magnetic field. Okay. So, in this case, you can use your finger to know the direction. So, if the current is flowing in the direction of your thumb, the magnetic field is in the direction pointed by your fingers. Okay. So, this is the Biot-Savart law. So, the field produced at any particular radius is given by this formula. So, it is proportional to the current and it is inversely proportional to the radius at which you measure the current. So, as I have told you, this is happening in real life in your brain. Even when you are learning the magnetism, your brain is firing and there is flow of current from one neuron to the other neuron. You are producing magnetic field as you are listening to this conversation, and that is one application. The second application is that this principle was used in one of the earlier forms of magnetic random access memory. So, we used this magnetic field to write information in MRAM. So, that was one another application.
I'm going to sprinkle some iron filings onto the plastic. I will now apply a current and I will have to tap the plastic to get the iron filings to move. And you can see how the iron filings have rotated to form circles around the wire, indicating the form of the magnetic field intensity generated by a current carrying wire.
Okay, if the current is flowing in this direction, the iron filings will follow the fingers. Okay. So, that is one way of producing a magnetic field, and we don't use that much in our labs. Okay. The second method to produce magnetic field is by creating solenoid and sending a current through the solenoid. You can produce magnetic field. So, I do not know, many of you would have come across Helmholtz coil in your laboratories. So, in Helmholtz coil you have a lot of wires wound in certain fashion. So, by sending a current through the Helmholtz coil, you can produce a magnetic field. So, there the field is given by this formula N I over L, where N is the number of turns and L is the length. So, we can also say N is the number of turns per unit length, and I is the current that you sent through the Helmholtz coil. Okay, so, sometimes you may wonder which side is north or south. So, you can use this mnemonics to understand which is the north pole or south pole of a Helmholtz coil. Let us say you look from one direction and the current is flowing in this fashion. Okay, so, this looks like north, right. So, this is the north pole. In the other direction the current will flow in the other way. So, this is the south pole. Okay. So, this is a mnemonics you can use to understand which one is the north or south pole. The third way, which is the most common way to produce a magnetic field, is to use an electromagnet with a ferromagnetic core. Okay. So, electromagnet with a ferromagnetic core is very similar to the solenoid that we saw in the previous slide, except that in this case we introduce a magnetic material into the core of the solenoid. So, this magnetic material has a property called permeability. So, this permeability can be 100 or 1000 depending on the material that you use. So, this permeability will multiply the magnetic field produced by a normal coil. Okay. Normal solenoid only produce a magnetic field of Ni/L. Okay. Whereas, when you introduce a magnetic material with a permeability mu r, the magnetic field is amplified by this factor. Okay. So, if you produce like 1 Tesla, 1 worsted with a coil, and if you introduce a magnetic material with a permeability of 1000 for example, the magnetic field will be amplified to 1000 worsted. Okay. So, this is the use of the ferromagnetic core. So, if you look at this picture, so we have 2 cylinders, right, there are 2 cylinders here. So, here we have coil. So, there are lot of wires wound here and here, and in between you can see a gray color cylinder. So, this gray color cylinder is the electromagnetic material, the ferromagnetic material. It amplifies the magnetic field by this factor, which is permeability. So, here the field strength depends on the current that we send, the number of coils per length, and it also depends on the permeability. Okay. So, normally this cylinder you see can be of 2 different shapes. Okay. So, it can have like flat edge on one side, and another side it may have a cone like structure. Okay. So, when you have this one, you can switch the directions of the core, ferromagnetic core. So, this red color thing what you see here is the ferromagnetic core. So, by switching, so you can make the 2 cones face each other, or you can make the 2 cylindrical parts face each other. So, you can achieve 2 different configuration. Okay. So, in this configuration, the magnetic field shown by these lines are over a narrow range, but the magnetic field lines are dense, you can see. Okay. That means, we can produce a strong magnetic field, but this field is uniform over a small area. Okay. So, that is one configuration. In the second configuration, we can produce a weaker field. You can see the number of flux line in the same area is lower. Okay. So, we produce weaker field, but this field is uniform over a large area. So, depending on what you want, whether you want uniform field or whether you want strong field, you can choose any of these configuration. Okay. So, these electromagnets are very common. So, you go to any lab where they work on magnetism, many of these labs will have electromagnet with a ferromagnetic core. Okay. So, these are some of the ferromagnet that we have in our lab in Singapore. So, this basically this slide tells you why we need a ferromagnetic core. So, if you just use a Helmholtz coil, you cannot produce a very strong magnetic field. On the other hand, when you introduce a material like iron or mu metal with a high permeability, the magnetic field gets enhanced by the factor mu r. Okay. So, that is the reason. Okay, let us do this question now. So, when this question comes, maybe they can focus the camera to this screen. Okay, I will stop after I get 35 answers. Now, 33. 34, 'Okay. Okay, all of the above happens is the correct answer. So, when you send a current through a wire, you produce heat because of the Joule heating, you produce a magnetic field, that is what I taught you, and of course, there will be a potential difference between the two ends. So, all of the above happens. Next question. Okay, I will stop now. Okay, all of you are right, very good. Next question. Okay, majority of you are right. The correct answer is you can enhance the magnetic field more efficiently by inserting a magnetic material with a relative permeability. Okay. So, I told you that the magnetic field purely due to current is N I over L. Okay. So, if you want to enhance the magnetic field by 100 times, you have to increase the current by 100, a factor of 100, okay, which is not efficient way. On the other hand, you just insert a magnetic material with a permeability of 100, then you can enhance the magnetic field. So, the efficient way is to insert a magnetic material with a high relative permeability. Okay, so, now let us move on to the next discussion. So, we learned that we can produce magnetic field by flow of charges. So, the charges can flow in a straight line or it can flow in a curved path. Okay. So, it can generate magnetic field, but we also have learned that we can produce magnetic field with a permanent magnet. So, if you bring a permanent magnet near a fridge, the permanent magnet will stick to the fridge, because the permanent magnet is producing a magnetic field. So, here we are not sending any current. So, why does the permanent magnet produce a magnetic field? So, this is the question that we will be discussing in the next few minutes, even until tomorrow. Okay. So, in solenoid you send a current and it produces magnetic field, and in the bar magnet also you can see a magnetic field. So, the north pole, south pole, they all look identical. Okay. So, even when we are not sending any current through the permanent magnet, we are still able to produce magnetic field. The reason is one case is classical electrodynamics. So, when you talk about sending current to produce a magnetic field, that comes under classical electrodynamics. But for understanding how a permanent magnet works, we need to understand some aspect of quantum mechanics. Okay. So, in this course I will not go too much into the quantum mechanics, because you would have all studied quantum mechanics before, but I will touch upon the basics. And also in this course I am not going to teach everything about magnetism, but what is needed for understanding the MRAM, okay, magnetic random access memory. Sometimes you all learn lot of aspects of magnetism. Quite often some simple facts are missed. Okay. So, I am going to teach the simple facts that are necessary for understanding the functioning of a magnetic recording or MRAM. So, the treatment of magnetism will be a bit different here. Okay. So, to understand the magnetism that comes with the permanent magnet or magnetic material, we need to understand some of the properties associated with electron, such as orbital magnetic moment or spin magnetic moment. So, these terms we will be using very often. So, in future, I mean for the next few days, I mean we are going to be together for another 8 days. So, in all those days, if I use the term magnetic moment, basically I am referring to a tiny magnetic dipole. Okay. So, you know that magnets have 2 poles. So, this is what we call magnetic dipole, right. So, moving forward for the next few days, when I say magnetic moment, I am talking about a tiny magnet which may look like this. So, but we do not draw like rectangle, draw north south pole, but simply we use symbol arrow. Okay. So, arrow like this represent a tiny magnet with a north pole. So, the arrow head is basically the north pole, and this tail is the south pole. Okay. So, we use this symbol arrow to represent magnetic moment. So, I will be drawing lots of arrows in the next few days. Okay. So, whenever I draw arrow, you remember that it is a tiny magnetic dipole. Okay. And the discussion from here on, I mean although I start this slide with the permanent magnet as the title, but whatever discussion we are going to do in the next few hours is not just related to permanent magnet, but it can be applied to many magnetic materials in general. Okay. Okay, let us do another question before we move on. Okay, all of you are right, very good. Next question. Next question you can answer anything other than ferromagnet. Okay. Okay. So, the key word here is attractor. Okay. So, you have chosen iron to be a magnetic material because you saw that iron got attracted to a magnet. Okay. So, that brings us to the next slide. So, I asked you to avoid the term ferromagnet because I want you to think like a common person, okay, not like a physicist who have studied some aspect of magnetism. Okay. So, if you ask a normal person who has not studied physics to describe materials into two types, then they will have only two types, right. One is a magnetic material, another one is a non-magnetic. Okay. So, how do they divide this? They divide this based on whether a material get attracted to magnet or it does not get attracted to magnet. Okay. So, when material gets attracted to magnet, they call it magnetic, and if the material does not get attracted to a magnet, they call it non-magnetic. So, this is the non-physics way of classifying materials on magnetism, but physicists have classified magnetic materials into 5 different types. Now, there is a 6th type which we can discuss if there is time, but traditionally there are 5 types of magnetism according to physics. Okay. So, the ferromagnetic and ferrimagnetic materials, they get attracted to magnet. Okay. So, that is what a common person calls magnetic, whereas there are some other materials which do not respond to magnet in a significant way, but they still respond to magnets in certain way. Okay. I will show you some videos to explain some of this aspect, and based on their property, physicists have given the names paramagnetic, diamagnetic and antiferromagnetic. Okay. So, for the next few hours we will be learning what differentiates these different materials and so on. Have anyone seen ferrimagnetic material? Okay, you have seen. Anyone else? Only one. Which one have you seen? YIG. Okay. YIG you have seen. Anything else? Pardon? Fe3O4 you have seen. Okay. Anyone else? Have anyone seen the old speakers with the black magnet? Have you seen? Or even the fridge magnet, the black fridge magnet, right? So, that is some kind of iron oxide, that is a ferrimagnet. Okay. So, you all know ferrimagnet, but you do not know that it is ferrimagnet. Okay. So, the black magnets are called ferrite. So, ferrites are ferrimagnets. So, we know that cobalt, iron, boron, they are all ferromagnet, and we have also seen lot of ferrimagnets, they also get attracted, and fridge magnets are ferrimagnets. Okay. So, you can see that it gets attracted to the fridge. So, this is what common people call as magnet but these are also magnetic, they respond to magnetic field in certain different way. Okay. So, from a lay person's perspective, only ferromagnetic materials are magnetic, ferrimagnetic materials also get attracted, and scientifically all materials respond to respond to a magnetic field in different ways. Okay. So, these are examples of paramagnetic materials, diamagnetic materials, antiferromagnetic materials, and so on. So, ferro and ferrimagnetic materials, they will be attracted to magnets. Paramagnetic materials will be weakly attracted to magnets. So, this weak is like very difficult to see. If you have a very strong magnet and you bring a piece of aluminum, then you will notice that the aluminum gets slightly attracted. Okay. But this attraction is very weak. At diamagnets get repelled by magnet, this again weak. Okay. So, people use some magnetometers to measure whether or to find out whether material is paramagnetic, diamagnetic, and so on, which we will learn later. But I want to show you this example that diamagnetic materials get repelled by magnet. Okay. If you take a frog, for example, frog has very few bones, very light bones, and the body of a frog is made up of around 80% water. Okay. Water is diamagnetic. Okay. So, in this experiment, what the researchers did is they got a 7 Tesla magnet to play with. So, it is on a Friday afternoon. So, this group basically Friday afternoon they have fun. Okay. So, what they decided to do, they put the frog on top of a 7 Tesla superconducting magnet. Okay, then they saw that the frog was floating. Okay. Because the frog has like 80% water, water is diamagnetic, and there is a magnetic field coming from the bottom of the magnet. Let us say this is the magnetic field is coming this way. They put the frog and the magnetic field repels the frog, magnetic field repels the frog. So, the frog floats. Okay. And that is what they see. So, usually when I see this video, some people ask why didn't the frog jump off, why was it floating? Yes. Why wasn't the frog jumping off? Why was it floating? Pardon? Yeah, it needs to kick into something to jump, right? It was not able to kick. There is nothing to produce a force. It cannot produce a force. Okay, so this is one example that the diamagnetic materials are repelled by magnet. So, that was a 7 Tesla magnet. Okay. Can we show the repulsion between?
What I'm going to show you today is how everything is magnetic. So we all know that yes, a magnet can attract another magnet, but what you might not have known is that everything is magnetic. Water, air, people, wood. So I'll show you. Repel the magnet and get pushed.
Kind of looks like you're touching it.
Not touching it.
Prove it. Oh, there you go.
Push it back. Not touching it. Not touching it. So water repels a magnet.
Okay, so you don't need 7 Tesla magnet to show that magnets repel diamagnetic material. Even when you use smart structures like this, you can see the repulsion between magnet and water, which is diamagnetic. Okay. So, let us do one question. Okay, most of you are right. Okay, there are a few wrong answers, but mostly all of you are right. So, ferromagnetic materials are strongly attracted to magnets, ferrimagnetic materials are also strongly attracted, paramagnetic materials are weakly attracted and diamagnetic materials are weakly repelled. Okay, so, moving forward, you will learn many new terms. If you have not learned magnetism before, you will learn many new terms, okay, and you will be learning about various types of magnetic materials, what their properties are, how they respond to magnetic field and so on. Okay, I briefly showed what is a magnetic dipole before. Basically, you have a magnet with 2 poles. So, this is what we call magnetic dipole, and if you haven't learned before, you would have seen electrical dipole before. So, it is very similar. So, magnetic dipoles generate magnetic field. So, where does that magnetic dipole come from? So, for that we need to understand the terms like orbital magnetic moment, spin magnetic moment and so on. Okay. So, as I told you before, whenever I draw an arrow is a symbol for magnetic moment. You can imagine like a tiny magnet with a north pole here, south pole here, something like that. Okay, so, first let us discuss orbital magnetic moment. So, you know that in atoms electrons go around the nucleus. So, you know that charges in motion produce magnetic field. This is what we learned a few minutes ago. We learned that when charges flow, they produce a magnetic field. So, in this case, the motion of electrons around the nucleus produces this orbital magnetic moment. Okay. So, the unit for magnetic moments is a Bohr magneton. So, when electrons flow around the orbital, then the electrons have certain Bohr magneton. Okay. So, one Bohr magneton has this value. So, 9.27 10 power minus 24 ampere square meter. Okay. So, this is difficult to understand. So, you can imagine a 10 microampere current flowing through a wire with dimensions 1 nanometer, 1 nanometer. Okay. Imagine such a current flows through a loop of 1 nanometer square dimension, that will produce certain magnetic field, and that is equivalent to 1 Bohr magneton. And okay, so the flow of electrons around the nucleus produces orbital magnetic moment. Okay, and this is probably the last slide. I am going to talk about orbital magnetic moment, because in most common magnetic materials that we use like iron, cobalt, nickel, in all these magnetic materials, the orbital magnetic moment is said to be quenched. Okay. So, this quenched is a quantum mechanical term. So, you can derive some equations, and finally, you will find that this orbital magnetic moment becomes 0. Okay. So, the quenched is the technical term to say that the orbital magnetic moment contribution is 0. Okay. So, that in simple words, quenched means 0. Okay. So, the orbital magnetic moment does not play a big role, but for the completeness I just briefly talked about it. So, what contributes to the magnetic properties of materials like iron, cobalt, nickel is mainly coming from the spin of electrons. So, yesterday we discussed various definitions of spin, but if you do not understand, just accept that electrons have spin, and the electron spin is like electron having certain magnetic property. Okay. So, you can say that certain electrons have north pole up, south pole down, certain electrons have north pole down, south pole up, something like that. Okay. So, this spin magnetic moment is the main contributor to the magnetic properties that we see in materials like iron, cobalt, nickel. Okay. So, we know that the electrons are filled in certain order. Okay. So, to understand the magnetic property of iron, let us take iron nucleus here. Okay. So, this is iron nucleus, and we are going to look at how the electrons are filled in different shells of iron orbits. Okay. So, we know that according to Pauli's exclusion principle, no two electrons cannot occupy the same quantum state, and we also fill the electrons according to Hund's rule. Okay. So, firstly the 1s shell will be filled with 2 electrons. So, one spin up, one spin down. Then we have 2s shell again filled with 2 electrons. 2p will have 6 electrons. So, 3 up, 3 down. Okay, up to 2p we have 3s, again one spin up, one spin down. Then after 3s we have 3p. So, 3 spin up, 3 spin down. So, after 3p, 4s will be filled. Okay. So, 4s will have one spin up, one spin down. So, iron has 26 electrons. So, we have filled 20 electrons. Okay. So, we are left with 6 electrons which will go into the 3D. So, 3D can accommodate 10 electrons. So, first it will be filled with 5 electrons up, and we will have 1 electron which is spin down. Okay. So, in all the other shells except 3D, we have compensated spin. So, let us say this contributes to certain Bohr magneton. So, that value is cancelled by the spin of the opposite type. So, there is no net magnetic moment in any of the other shells except 3D. Okay. So, each electron has a magnetic moment of 1 Bohr magneton. Okay. So, here all it will become 0 0 0, but here you see there are 5 spin up electrons and 1 spin down electron. So, we will have 5 minus 1 Bohr magneton. Okay. So, we can simply say that if you take one iron atom, isolated iron atom will have a magnetic moment of 4 Bohr magneton. So, you can consider this as a unit for magnetic moment. Okay. So, this is one kind of unit for magnetic moment. For distance we use meter, kilometer, mile. So, in a similar sense you can take this mu b as the unit for magnetic moment. So, if you take one isolated atom of iron, so it will have 4 Bohr magneton. So, this is the magnetic moment of one isolated iron atom. So, now let us look at the materials that we know. Iron is a ferromagnet. Iron has 26 electrons. So, 5 up, 1 spin down, 5 spin up. So, we have 4 unpaired electrons. So, we can say that iron has 4 Bohr magneton. Cobalt will have 3 unpaired electrons. So, if you take isolated cobalt atom, it will have 3 Bohr magneton. So, nickel has 2 unpaired electrons in the d shell. So, we can say nickel has 2 Bohr magneton. So, in some sense we can roughly infer that if you bring a piece of iron next to magnet, iron will be strongly attracted than cobalt and then nickel. Okay. We can roughly infer this behavior just from the simple perspective of how the electrons are arranged in the d shell. Okay. But it gets a bit tricky. You take chromium for example. Chromium also has 5 unpaired electrons. So, chromium atom also should have 5 Bohr magneton. Manganese also has 5 unpaired electrons, it should have 5 more magnetron. But if you bring a piece of chromium next to a permanent magnet, you will see chromium does not get attracted, manganese does not get attracted to magnet. So, what happens? There is something else missing here. Okay. So, only some elements with a certain magnetic moment, they are magnetic, but some elements with a certain magnetic moment are not magnetic. Okay. So, something comes, something else we need to take into picture. Okay, let us say we put many atoms of say any of these elements together, there are many possibilities. So, one possibility is that you put many atoms with magnetic moments next to each other, they all lie parallel to each other, this is one possibility. Okay, the second possibility is that you put these magnetic moments next to each other, they align anti-parallelly. This is another possibility. Third possibility is that you bring many atoms with magnetic moments next to each other, they do not have any preference, they are randomly aligned in any direction. Okay. So, all these three possibilities exist. Okay. And these possibilities are the one that determines whether a material is ferromagnetic or antiferromagnetic or paramagnetic. Okay. So, there is some phenomena that makes the neighboring magnetic moments to be parallel or neighboring magnetic moments to be anti-parallel, or it does not do anything. Okay. Neighboring magnetic moments are just random. Okay. So, what is that property that makes, that brings this phenomena was not known until say 100 years ago. So, before 100 years ago, people did not know what makes the neighboring magnetic moments parallel or anti-parallel and things like that. So, people had various explanation. So, one of the explanation was given by Weiss. This theory is outdated. So, he thought that there is some internal magnetic field inside material, and that magnetic field is the one that aligns the neighboring magnetic moments parallel to each other. Okay. So, Weiss thought that there is some internal magnetic field inside material, and that is what makes the neighboring magnetic moments parallel to each other. Okay. So, that was the concept, but if you do analyze, this field will be very strong. Okay. The field that you require to force the neighboring spins of say 2 iron atoms parallel to each other will be like 1000 Tesla, which is like 100 million times stronger than the Earth's magnetic field. Okay. So, this theory is now outdated. So, around 100 years ago, Heisenberg came up with the quantum mechanical description of what makes the 2 neighboring spins to be parallel to each other. Okay. So, we will not go into the quantum mechanical derivation of everything, but we just come to the result. Okay. So, Heisenberg states that let us say we have 2 spins S1 and S2. These are vectors. So, the energy between these 2 spins will be given by this formula. Okay. So, this J is called the exchange integral. So, this comes from quantum mechanical derivation. So, the energy between 2 spins S1 and S2 will be given by this formula, J is exchange integral. Okay. If J is positive, for example, then the energy will be low when S1 S2 cos theta, right. So, it is a dot product. So, when theta is 0, then this is a positive number. When theta is 0, this will be a positive number. So, if J is positive, energy will be low, because it is a negative term. So, if J is positive, S1 and S2 have to be parallel, because theta is 0. Okay. So, this is one condition. If J is negative, then the energy is minimum when S1 and S2 are anti-parallel. So, when theta is 180 degree, cos theta will be minus 1. So, S1 S2 will be negative, and if J is also negative, this whole thing will be again positive, then we have a negative. So, energy will be low. Okay. And if J is 0, there is nothing in the system to make the spins parallel or anti-parallel. So, if you take room temperature, at room temperature is 300 Kelvin, let us say. So, there is a kBT thermal energy. Thermal energy is temperature in Kelvin multiplied by Boltzmann constant. So, there is a thermal energy which will make the magnetic moments to flip as a function of time. Okay. So, if there is no energy to keep the two spins parallel or anti-parallel, the neighboring spins will be fluctuating as a function of time. Okay. So, this brings rise to at least 4 different types of material. Okay. So, the first case where the spins are parallel to each other, they are ferromagnetic. The second case, when J is negative, the spins are anti-parallel to each other, they belong to anti-ferromagnetic category. And when there is no, when J is 0, the spins are fluctuating as a function of time. So, they are random in time as well as in space. So, this brings rise to the paramagnetic property. Okay. So, now this slide summarizes how the spins are organized in ferromagnetic material and antiferromagnetic material. So, in the case of ferromagnetic materials, the J exchange integral is positive, and that makes the spins parallel to each other. So, this is the ferromagnetic material. Okay. In the case of antiferromagnetism, the neighboring spins are anti-parallel. This is the lowest energy state. Okay, then there is a special case of antiferromagnetism. So, in this case, let us say I have all chromium atoms, okay, all are chromium. So, this will have 5 Bohr magneton, this has 5 Bohr magneton, and so on. So, all of these tiny atoms have equal magnitude of Bohr magneton. So, you can see that they cancel each other. Okay. So, 5 minus 5, 5 minus 5, and so on. So, the net magnetic moment will be 0, because they are equal in magnitude, opposite in direction. But ferrimagnetic material are a subclass of this one, where the difference is that the neighboring spins have different values of magnetic moment. For example, this atom may have 5 Bohr magneton, this atom may have 2 Bohr magneton. So, 5 2 5 2 5 2 and so on. Okay. So, if you add them together, so 5 minus 2 3, here we have 5 minus 2 3 and so on. So, it will keep adding to a large value. So, when you put lot of atoms together, the neighboring magnetic moments do not cancel as it happens here. So, in the case of antiferromagnetic material, you put even billions of atoms, the neighboring moments are antiparallel, they are equal in magnitude. So, as you keep adding, they will total it will be 0 magnetic moment. However, in the case of ferrimagnetic materials, they are of opposite, I mean they are opposite direction, but they are of different magnitudes. So, the net magnetic moment does not get cancelled. So, it will add up to a very large number. So, here I am using the term magnetization without defining what is magnetization, but I have defined magnetic moment. So, we can use the net magnetic moment is very large for ferrimagnetic material and ferromagnetic materials. So, here again like if these are iron atoms, right. So, 4 Bohr magnetron, 4 Bohr magnetron. So, you keep adding 4 plus 4 plus 4. So, this net magnetic moment will come to a very large value here. Here it is 0, here again it is still a large value. Okay. So, these materials are called ordered magnetic materials, because the spins have certain order, either they are parallel or they are antiparallel. So, these are called ordered magnetic materials. Yeah. Yeah. Yeah.
So these ferrimagnetic materials always contain the compound, or the single metal can be ferromagnetic?
Single material I think cannot have ferrimagnetism, because you are talking about one type of atom, right. So, how can one type of atom have two atomic moments? So, it is not possible. So, most often, so for example, you say gadolinium cobalt. So, gadolinium has one type of magnetic moment, cobalt has another type of magnetic moment, they are in opposite direction, because of that they will have some net magnetic moment. So, this can be like gadolinium cobalt, something like that, or there are ferrite, lot of ferrites, there again like two sides there will be different magnetic moments.
Ferrimagnetic we can always see in the compound materials only, not in single materials.
Compounds or alloys, yeah. There is no single element that has ferrimagnetic property, yes. So, like gadolinium, cobalt, those are alloys, right. You do not have a crystal structure, I mean they are not compounds, you can mix any composition of gadolinium, cobalt. Okay, there are some theories which people predicted, I mean people used to explain why certain magnetic materials have positive J, why some materials have negative J, and this curve is called the Bethe-Slater curve. So, in this case the J is positive or negative, depends on the interatomic spacing or radius of the d shell and so on. Okay. These are some of the earlier theories. So, we studied the case of J positive or negative, which leads to ferro, ferri and antiferromagnetic materials. So, J is positive or negative, we have ordered systems. When J is 0, we have paramagnetic materials, because there is nothing to force the neighboring magnetic moments to be parallel or antiparallel. So, in the case of paramagnetic materials, the spins of neighboring atoms are in random direction, and they also fluctuate as a function of time. So, if you observe say a set of spins at time t 1, they are like this at time t 1. So, you observe them at time t 2, you can see that they look different, because they keep fluctuating as a function of time. And the second point is even the ferromagnetic material or antiferromagnetic material, all the ordered materials will become paramagnetic above certain critical temperature. So, in the case of ferromagnetic materials, when they go above certain temperature called Curie temperature, they will become paramagnetic. So, if you take antiferromagnetic materials, heat them above certain temperature called Néel temperature, they will become paramagnetic. Okay, so, this is basically a description of different types of materials that we have learnt. So, ferromagnetic material or antiferromagnetic material, the magnetic moments does not fluctuate much as a function of time, whereas you notice that the paramagnetic material had magnetic moments fluctuating as a function of time. Okay, let us do some questions. Sorry. Okay. Are there any questions here? No. Okay, the correct answer is a magnetic dipole. Okay. So, when I say magnetic moment, I am just talking about an arrow which represents a magnetic dipole. Okay. So, I am not talking about anything going around anything. Okay, next one. Okay, majority of you are right. Okay, the magnetic moment of ion atoms come from the uncompensated spin. Okay, it is not just spin. Okay, the spin can be compensated, right. If you have 5 up 5 down, then the net magnetic moment is still 0. Okay. So, in the case of ion atom, I showed you that there are 6 atoms in the D. So, 5 are up, 1 is down. So, we have a net uncompensated spin moment of 4 Bohr magneton. Okay. So, this is the correct answer. Okay, almost all of you are right. In antiferromagnetic materials, the neighboring spins are anti-parallel. Next one. Okay, so in ferrimagnetic materials, there are at least two types of atoms with different magnetic moment values. So, this answer your question. Okay. So, there are at least two types of atoms with different magnetic moments, and they are aligned anti-parallel direction. So, I should have seen equal number of votes for both, okay, because both are correct answers. Okay, now let me play this video. Okay, so I am playing this video to teach you some concept. So, I want to know whether you got it. Okay. So, please type your answer here. What do you see happening there? Okay. I am trying to go through this one, magnetic alignment. Okay, anyway, what you answered is not important for this discussion. Basically, this video I played to bring out the next concept, which is called magnetization. So far I was discussing magnetic moment. So, magnetic moments or the magnetic properties of atoms. So, we were talking about atomic magnetic moments. So, what happens when you put them together? So, they may add up like in ferromagnetic materials. So, I told you that 4 Bohr magneton, 4 they add up, right, to a large value. In ferrimagnetic materials also they add up to a large value, and in the antiferromagnetic materials they cancel out to be 0. So, we have some term to define what happens when you put many atoms together and how they add up. So, it will be a very large number, right. So, instead of having a very large number, so we want that number to be independent of how many atoms you have. Okay. So, we have a term called magnetization. So, magnetization is basically, let us say you take some atom, it has magnetic moment m I, then let us say your material has n number of atoms. So, you add the magnetic moment of all the atoms 1 to n. Okay. So, if you have like billions of iron atoms, so it will be like 4 plus 4 plus 4 plus like that. So, 4 billion, then divide by the volume of the material. Okay. So, we have this definition called magnetization. Okay. So, this is an easy number to understand, and this will be independent of the material's volume or weight. Okay. In this case volume. So, in a material of certain volume V, you have n atoms. So, what you do is like you add the magnetic moment of all the atoms and divide by the volume, then you get a number, and that is what we call magnetization. So, I am quite used to the CGS unit. So, in CGS unit basically we use EMU per cubic centimeter. So, this is the volume. Okay. Then, so this is the volume you see here. Okay. And this EMU is the unit for the magnetic moment in CGS unit. So, this is one definition, magnetic moment per unit volume. Okay. People also do this summation 1 to n m I and divide by the mass of the material. Okay. So, that is expressed in EMU per gram. So, there are some people who study magnetic properties of powders. So, what they do, they measure the magnetic moment of the material, then they measure the mass of the material in gram. So, magnetic moment divided by the weight, that gives EMU per gram. So, some people use EMU per gram, some people use EMU per cc. These are CGS units. I am very familiar with the CGS. So, I am using this, but there are SI units for magnetization. So, when you do this, this becomes a material property. Okay. For example, let us say I have a piece of iron. I do not need to say what is the atomic magnetic moment of iron, but iron will have certain say 2200 EMU per cc, something like that. Okay. So, when you have a definition like this, magnetization, then you can express the magnetization of many different materials using the units like EMU per cc or EMU per gram. Okay. So, this is the definition for magnetization. Then normally when we measure, we also have another term called saturation magnetization. So, this is the largest magnetization a material can have. That means, when you apply very large magnetic field, all the magnetic moments point into certain direction, then you measure. Okay, that is called saturation magnetization. So, the value I showed here is basically the saturation magnetization of iron, which is around 2200 mu per cc. So far I was telling you that iron has 4 Bohr magneton. Okay. One Bohr magneton is this much mu, okay, and 1 gram of iron will have so many iron atoms. So, if I take 1 gram of iron and calculate the EMU per gram based on 4 Bohr magneton, okay, I will get a value of 400 EMU per gram. Okay. So, this is based on the fact that each iron atom has 4 Bohr magneton. Okay. However, if you measure experimentally, I give you a piece of iron, ask you to measure the saturation magnetization of iron, you will measure it to be something like 220 mu per gram. Okay, there is a huge discrepancy. So, so far I have been teaching you that each iron atom has 4 Bohr magneton, and I use this value to calculate the saturation magnetization of iron, then I get some number 400 mu per gram. But I give you a piece of sample iron, you go and measure, and you come back with the result of 220 mu per gram. Okay. So, somebody should be wrong, right? Either your measurement is wrong or I am wrong, right. So, there is some discrepancy here. Okay. Anyone has any idea what is the discrepancy? No, not nothing to do with the domain here. Pardon? Temperature, no. Yes.
Calculation is from the bare atom, so it
Yeah.
is very localized picture.
Yes.
Whereas in a T as a compound, it will have a kindred behavior.
Yes. So far I was talking about just taking simple atoms, but when you have a piece of iron, right. So, you have band structure coming into picture. So, bands form, then you have one spin up band and one spin down band. So, there is a density of states coming into picture. Then based on this picture, you will get this one. Okay. You will get the value of 220. Sorry, I am going in the wrong direction. Okay. So, based on this one, you will have 220 mu per gram. Okay. So, this is the correct picture. So far I was giving you a very simple picture of talking about single atoms of iron, but in reality when you put materials together, there is a band structure, and based on the density of states you see in the material, the difference gives rise to 220 mu per gram. So, this is the accurate picture. The simple picture is for easier understanding, but this is the realistic picture. So, sometimes people ask like whether you can make ferromagnetic materials only based on iron, cobalt or nickel. Most often we do that, we take iron, cobalt or nickel, then dope with something or make compounds out of these materials, and that is how we make ferro or ferrimagnetic materials. But there are many other ferromagnetic materials without iron, cobalt or nickel. So, for example, manganese, aluminum, chromium, platinum 3 and so on, they are also ferro or ferrimagnetic materials. Okay. They have no iron, cobalt, nickel. Okay. So, what determines whether a material will be magnetic or not? depends on the band structure. So, you have to come up with this kind of band structures to understand whether a material will be magnetic or not. Okay, so, here I show you some numbers related to iron, cobalt and nickel. So, what is important to see here, you can just notice that these values, for example, iron has a saturation magnetization of 1714 mu per cc, cobalt has 1422, nickel has 484. These are more or less very similar to what we studied before. For example, I told you that this one 4 magneton, 3. You can notice that the trend is similar. So, this is larger, this is medium, this is smaller. Okay. Okay, let us do some questions. Most of you are wrong. Two point two, 1.7 increasing saturation magnetization. So, it should be BCA. Yeah. So, BCA is the correct sequence. So, many of you are wrong. So, I was confused. So, I asked you to arrange in the increasing order, right. By the way, these numbers 2.2, 1 and 1.7, these are the Bohr magnetons of right here. Okay. Because this one I cannot write here. It's okay, no need. Anyway, I don't need to write. Basically, 2.2 Bohr magneton is the magnetic moment per atom of iron in the band structure. Okay. So, in a single atom, iron atom has 4 Bohr magneton, but if you put them together in a material, in a piece of iron, 2.2 Bohr magneton per atom is the magnetic moment of iron. Then nickel is roughly 1 Bohr magneton per atom in a material, in a solid. So, in the case of cobalt solid, cobalt atoms will have 1.7 Bohr magnetron per atom. So, these are realistic examples. So, iron, nickel and cobalt. So, after a few slides we will take a break. So, I told you that ordered materials will become paramagnetic after certain temperature. So, this is a piece of ferromagnetic materials, and here I am measuring, let us say until this point, this curve is magnetization. So, I am measuring the magnetization of a piece of iron as a function of temperature. So, as the temperature increases, the magnetization decreases to 0 value. Then after this value, I am not measuring magnetization, I am measuring another property. I will teach you this later. So, this property increases with temperature. Okay. So, at this point, magnetization becomes 0. And this temperature is what we call Curie temperature. Okay. So, if you increase temperature beyond Curie temperature, a ferromagnetic material becomes paramagnetic. Okay. So, different materials have different Curie temperature, not important. So, let me play this video. So, here is a paper clip, this is a magnet, this is a string. So, the string has a tension force because the clip is attracted by the magnet. Okay, now, he is heating the clip's temperature increased. So, it is going beyond the Curie temperature, it is not a ferromagnetic material anymore, it becomes a paramagnetic material. So, there is no force of attraction. So, there is no tension in the string. So, the clip just falls down. Let us say the clip is here, clip is cooled down now clip is at room temperature. Now, I bring it next to magnet, what will happen? The clip will be attracted or not? Yes or no? Yeah, it will be attracted. Okay. So, this curve is more or less you can say almost no hysteresis. So, you go this way, I mean some materials will have some hysteresis, but so normally you go up, then you cool down, most likely you are going almost in the same path. Okay. So, ferromagnetic material will become paramagnetic above Curie temperature, but if you cool down, it will be still ferromagnetic. Okay. So, in your school days, you would have learned that if you have a magnet, you do not heat it, because after heating you will lose the magnet. Why is it? Here I am telling you that you heat, it becomes paramagnetic, but if you cool down, it is still ferromagnetic. But in your school days, your teacher or someone would have told you not to heat a magnet. Okay, think about it, we will come to that later. Okay, this is the summary of what we learned so far. So, this is a mind map of what we learned so far. So, I introduced two concepts, that electrons have orbital moment and spin moment. That orbital moment is mostly not coming into picture, only in rarer materials orbital moment has some role, but in materials like iron, cobalt, nickel, spin moment is the one that leads to magnetic properties. So, when there are atoms with unfilled shells, They can lie parallel to each other or anti-parallel to each other, and we will have, when they are parallel to each other, we will have ordered systems. When they have no specific order, we have paramagnetic material. Okay. And when there are atoms with filled shells, they belong to diamagnetic materials. Okay. So, this is a mind map of what happens in the atomic scale that leads to different properties of material. Okay, we will take a short break, then come back to the rest. Maybe we will take 10 minutes. Now, it is 57. So, we will come back by 12:05. Tea break, is it? Then it should be longer, right? Okay, then maybe 12:10. Okay, 12:10. Come back by 12:10.
Every day we have a break, 15 minutes.
15 minutes.
Whenever.
Okay.
I had a question at slide 43. When
not working. Maybe, oh, it's connected. No, it's okay. You put it there. Put it there, please. Hello. Okay, let's resume. So far we have been learning about few different types of material. So, we can classify materials based on how they respond to a magnetic field. So, we learned that paramagnetic materials are weakly attracted to magnets, diamagnetic materials are weakly repelled, ferromagnetic materials and ferrimagnetic materials are strongly attracted. Antiferromagnetic materials are also very similar to paramagnetic materials in the sense that they are not strongly attracted. Okay. So, we call only this as ferro or magnetic materials because they are strongly attracted. So, I described how the spin configurations look like in ferromagnetic, ferrimagnetic, antiferromagnetic materials and paramagnetic materials. We did not touch on diamagnetic materials, but that you can do as a homework. So, just take a screenshot. You watch this video later, this is a homework. Okay. So, if materials are not strongly responding to, you want to, I will give you the link later. Okay. So, if paramagnetic materials or diamagnetic materials are weakly responding to magnets, how do we measure the magnetic properties? So, typically in most of the labs where they do research on magnetism, we have a magnetometer called a vibrating sample magnetometer. Okay. So, these are sensitive measurement systems with which we can measure very sensitive information about magnetic materials. So, normally you bring magnet next to paramagnetic material, you cannot see the attraction because the force of attraction is not that strong, but with these sensitive magnetometers we can measure the magnetic properties of diamagnetic material, paramagnetic material, ferromagnetic material, antiferromagnetic materials and so on. Okay. So, vibrating sample magnetometer or VSM is a commonly used measurement system for measuring magnetic property. So, when we measure magnetic property, we typically measure the magnetization M as a function of applied field H. Okay. So, you learnt that the magnetization M is the sum of magnetic moments divided by volume or weight, mass. Okay. So, we typically measure magnetization or magnetic moment as a function of applied field. Okay. So, here the applied field H is provided by the electromagnet. So, we learnt electromagnet before the break. So, you have coil, then you have a ferromagnetic core. So, the ferromagnetic core produces a magnetic field. So, in this case we have an electromagnet, this is the core, ferromagnetic core. So, the magnetic field either goes from this side to the other side. So, either the field can go this way, or if you change the current direction in the coil, you can make the magnetic field to go from this side to the other side. Okay. So, you can change the direction of the magnetic field, and by changing the strength of the current that you pass through the coil. So, you learn that the magnetic field is this, right. So, if you change the current, the value of the current, then you can change the magnetic field. Okay. So, you can change the direction of the magnetic field and the strength by changing the current direction and the magnitude of the current. Okay. So, typically we can sweep the magnetic field inside this region from say minus 20 kilovolt to plus 20 kilovolt. These are typical values. So, in some equipment maybe this is 10 kilovolt, some equipment this may be 30 kilovolt. Okay. So, we sweep the field. So, for measuring the magnetic properties, we usually plot magnetic moment or magnetization as a function of applied field. Okay. So, this field can be increased or decreased or changed to another direction and reduced to 0. Okay. So, we can sweep the magnetic field, and we need to measure magnetic moment or magnetization. Okay. So, to measure the magnetic properties, we use Faraday's law of induction. Okay. So, you know that Faraday's law of induction states that if you have a time varying magnetic flux and if there is a pickup coil next to the time varying magnetic flux, you will produce a voltage. Okay. So, this voltage is proportional to the time varying magnetic flux. So, we use this Faraday's law to measure the magnetic property. Okay. So, here you notice that we have the sample. Okay. This orange color one is the sample that we want to measure. Let us say it is magnetized in some direction, let us say this is north south or sorry. Let us say one of them is north, another is south, for example. So, you know that it will generate some magnetic field, right. So, there will be some flux lines coming out of your sample. So, when you vibrate this sample, these flux lines are cutting these pickup coils. So, these blue things that you see, these are pickup coils. So, the pickup coils will see a time varying magnetic flux. So, your sample is the one that produces the magnetic flux and that reaches the pickup coil, and because your sample is made to vibrate, there is a time varying magnetic flux at the pickup coils. So, the pickup coils will generate a voltage. Okay. So, this voltage is the one that you use for the magnetization. For example, what you do is you will put a known sample. For example, you have a piece of nickel. Let us say this nickel sample has 1 EMU. Okay. At first what you do, you place the nickel sample here, you vibrate and look at the voltage. Let us say 1 EMU produces 1 volt. Okay. Then you go back, then you know that 1 volt means 1 EMU. Suppose you get 100 microvolt, then you know that 100 micro EMU. So, you do the calibration with a known sample. So, first you place a known sample, then you know that this particular EMU generates a particular voltage, then you go back. So, if one voltage gives you 1 EMU, then 100 microvolt is like 100 micro EMU, something like that. Okay. So, this is how we measure the magnetization using vibrating sample magnetometer. Okay, typical vibrating sample magnetometer will look like this. So, this is the one we have at NTU. So, this is the magnet, electromagnet. So, the blue color region is the one where we have the coils. So, the coils are wound here, and this shiny silver color thing is the one, the core, ferromagnetic core, and somewhere there we have the pickup coils. Okay. So, the blue color one is the electromagnet, and this shiny thing is the core, and we have some pickup coil somewhere there. Okay. And we place the sample on this vibrating rod. Okay. There is a rod, you can see the sample is somewhere here, and we vibrate this rod using a vibrating assembly. So, this can be a speaker, or it can be some mechanical transducer to vibrate the sample. Okay, so, the pickup coil produces some voltage, that voltage is collected by this system. So, this system will control everything. So, it will sweep the magnetic field, it will collect the signal from the pickup coil, and you can finally get the plot of magnetization versus. So, normally when you measure, you get magnetic moment, okay, because you put a sample, if you do not know the weight or volume, what you collect is basically magnetic moment, then later you divide by volume or mass of the sample to get EMU per gram or EMU per cc. Okay. Yes.
Why we are putting the vibrating rod instead of the fixed rod, stationary rod?
Because you want to produce a time varying flux. So, we are relying on Faraday's law of induction to measure the signal. So, you get a signal only when this magnetic flux of the sample vibrates. Okay. So, you cannot have stationary. Any other question? Okay, so, this cartoon of what is happening. So, you place a sample, sample produces a stray magnetic field, and when you vibrate the sample, you okay, your sample vibrates, then you see that there is a time varying magnetic flux sensed by the pickup coils. So, you see there is some voltage sensed by the pickup coil. Okay. So, this is how we measure magnetic properties. Okay. So, so far we have been learning some fundamentals of magnetism, but we have not learnt like how do different materials respond to a magnetic field. So, I gave you a very simple picture that diamagnetic materials will be repelled by magnet. Okay. But if you place a diamagnetic material inside vibrating sample magnetometer, what property will you see? How will the MH curve will look like? So, all those things we have not learned. So, we will learn that. Then we learnt about ferromagnetic materials a bit. Are there different types of ferromagnetic materials? We have not learnt. Then okay, we make bar magnets from magnetic materials, but why only certain type of materials make them permanent magnet, why a paper clip is not permanently magnet. So, all those things we will learn in the next few minutes. Okay, first let us go on to learn about how do different magnetic materials respond to a magnetic field. Okay, so, I told you that when we place a sample inside a VSM, we measure magnetic moment or magnetization as a function of applied field. So, let us assume that we are always measuring magnetization, okay, not magnetic moment, but let us say we measure magnetization. Okay, let us say I put a piece of aluminum inside the vibrating sample magnetometer, and I trace the magnetization of aluminum as a function of applied field. So, when the magnetic field is 0, the magnetization is 0. As I increase the magnetic field, the magnetization will start increasing. Okay. So, as I keep increasing, it will go up and it will follow the straight line, and when I reduce the magnetic field, it will just go back to 0 in the same path. Okay. The path is the same. So, this is the typical behavior of paramagnetic materials. So, materials like aluminum, ruthenium, these are all paramagnetic materials. They will show positive slope of MH curve. So, we can define the slope as chi susceptibility. So, in this case basically is m over h or delta m over delta h. So, we use this term susceptibility chi, which is basically the slope of the MH curve when we deal with non-ferro or non-ferrimagnetic materials. So, whether it is a paramagnetic material or diamagnetic material, antiferromagnetic material, we deal with susceptibility. So, do anyone remember where we saw this chi before? Yeah, correct. So, when I showed you the Curie temperature, I showed you this graph and this one. So, this I told you this is magnetization, and from this point onwards is susceptibility. Okay. So, susceptibility is basically the slope of this MH curve, and it is positive for paramagnetic materials. Let us say now I put a piece of copper inside or silicon inside the vibrating sample magnetometer and measure the magnetization as a function of magnetic field. Initially the magnetization is 0, but once I increase the magnetic field, the magnetization will start decreasing. Okay, it will follow this path, and if I start reducing the magnetic field, again it will come back to 0 along the same line. Okay. No, the path is the same for going down and coming back up. So, diamagnetic materials have a negative slope or negative susceptibility. Okay. Ferromagnetic material is a different issue, we will see later. Okay, suppose I give you a piece of material, okay, and ask you to find out whether this material is paramagnetic or antiferromagnetic. How will you find? Okay, that is tricky, right. So, both the materials will have like very weak response to a magnetic field. So, let us say their slope may be something like this. Okay. So, how do you differentiate between para and antiferromagnetic materials? So, for that usually we need to do a temperature dependence measurement of susceptibility. For example, if you measure the temperature dependence of paramagnetic material, you will have this 1 over chi T behavior. For example, at temperature T1, I have this slope, another temperature T2, I have another slope. If I measure the same curve at temperature T3, I have another slope. Okay. So, I have various slopes, okay. Another, let us say T10, I have another slope, something like this. Okay. I mean, this is not in order, some random number. Okay. So, I have various slopes, and if I plot the slope as a function of temperature, I will have this curve. Okay. It will follow 1 over T behavior, and this is a typical sign of paramagnetic material. Okay. And if I do the same, I measure this slope, negative slope of diamagnetic material at different temperature, the slope will not change. Okay. The slope is constant. At any temperature, the slope remains the same. So, if I give you some, okay. So, constant slope is the indicator of diamagnetism. Constant slope as a function of temperature is an indicator of diamagnetism. Now, let us come back to the question, how will we distinguish between paramagnetic material and antiferromagnetic material. Okay. So, in the case of antiferromagnetic materials, I told you that above a certain temperature, these materials will not have ordering, they will have paramagnetic. Okay. So, antiferromagnetic materials will behave like paramagnetic materials above certain temperature called Néel temperature, but below Néel temperature their susceptibility has a different behavior. Okay. So, you will see a peak in the temperature dependence of susceptibility as a function of temperature. So, if you see a peak like this is an indicator of antiferromagnetism. Okay. So, I give you a piece of sample, what you do? You go to the lab, measure the susceptibility as a function of temperature. Okay. So, let us say one sample gives you this behavior, okay, another sample gives you this behavior, then you can say that this green sample one that gives the green line is paramagnetic, and the one that gives you the red color behavior is antiferromagnetic. Okay. So, this is how we can distinguish between paramagnetism and antiferromagnetism. So, this peak is an signature of antiferromagnetic materials. You can skip this one. Okay, let us do some questions. Okay, most of you are right. We have some work on the basis of Faraday's law. Okay, next question. Okay, positive susceptibility is from paramagnetic material. Majority of you are right. Next one. Okay, most of you are right. Okay, so far we have learnt how the MH curves of different materials like paramagnetic, diamagnetic and antiferromagnetic materials will look like, but we haven't learnt how the MH curve of ferro or ferrimagnetic materials will look like. Okay. So far the cases were either they were increasing or decreasing as a function of magnetic field. Okay. But if you place a ferromagnetic or ferrimagnetic material inside a vibrating sample magnetometer and you try to measure the MH curve, it will not be a straight line. Okay. It will show a different behavior, what we call hysteresis loop. Okay. Okay, so let us say you start, let me stop here. Let us say you start increasing the magnetic field. Initially the magnetization will increase to certain value. Okay. It will not go straight line, it will go in some curved line, it will go up. Okay. Then you reduce the magnetic field. It is tracing a different path. Okay. Now you go to the other direction, you reduce the magnetic field, again it traces another path. Okay. So you see that it creates a loop. Okay. And this loop is called the hysteresis loop. Okay. So this is a typical behavior of ferro and ferrimagnetic materials. Okay. So you start from here, for example, 0 magnetization. As you increase magnetic field, you see that it goes in a non-linear fashion. It reaches the saturation and when you reduce the magnetic field, it takes another path, okay, it reaches saturation in the other direction. You reduce the magnetic field, then change the direction, you see that it traces another path. So, basically you have a loop, and this loop is called hysteresis loop, and this is a typical behavior of ferro and ferrimagnetic materials. So, from this loop we can extract many different parameters, and these are very useful parameters when you design a material for magnetic recording or material for MRAM application. These parameters that you get from the hysteresis loop are very important. Okay. So, the first concept that you need to learn is saturation magnetization. So, usually shown by this symbol MS, means saturation magnetization. So, when you apply sufficiently large field, so very large field, then the magnetization of a sample reaches saturation. Okay. It increases, then at some point it saturates. Okay. So, this saturated value is called saturation magnetization, and when you reduce the magnetic field, so you are reducing at this point the magnetization is 0, applied field is 0, there is no 0, there is no magnetic field, but still some magnetization is remaining in the same direction. Okay. So, this remaining magnetization is called remnant magnetization. So, remnant magnetization MR. Then let us say you change the direction of magnetic field, reduce, you keep, now you are changing the magnetic field in the other direction. So, at some point of time the magnetization becomes 0. Okay. So, when you see a hysteresis loop, it has 4 quadrants. This is typically 0 0. Okay. This is typically 0 0, means the magnetization is 0 and the magnetic field is 0. Okay. This coordinate means magnetization is 0, field is also 0. So, typically this side is a positive field, this side is a negative field, and this upper side is a positive magnetization, and this is negative magnetization. Okay. So, when you come to this field, the magnetization is 0. Okay. So, y axis is magnetization, x axis is H. So, y axis is 0, which means magnetization is 0. Okay. So, this field, you can see this is a certain field, right. So, this field at which magnetization becomes 0 is called coercivity. So, this is another important parameter, and if you go further, again you will reach saturation. So, the magnetization saturates again. Okay. So, this value and this value are same, but different magnitude. Okay. Either you call this as saturation magnetization or call this as saturation magnetization. This will be symmetric. And normally this is also symmetric. Okay. There are some cases where this HC is not symmetric, but normally the coercivity also is symmetric. Okay. So, you can imagine this loop now, you have MS, MR and coercivity. These 3 are very important parameters. So, usually what I do is ask my students to close the eyes, trace hysteresis loop in your brain, then assign these 3 points MS, MR and coercivity. Okay. These are very important parameters. Okay. So, by placing a ferro or ferrimagnetic material inside a VSM, we can trace this loop and get these parameters like MS, MR, coercivity and so on. So, in some field, for example, magnetic recording, we also have another field called nucleation field. So, at this field what happens, the magnetization at this field is actually 95% of saturation magnetization. Okay. So, this may not be that important, but these three are very commonly used terminologies. MS, MR and coercivity are important. Okay. So, let us do a recap of what we learnt about hysteresis loop. Yeah, the book lab shows some other question not shown in this picture. Let us do the book lab question. Okay, it's open now. Okay. Only 4 of you are right. Only 4 are right. So, which 4? This one or this one? Huh? Yeah. So, only 4 of you are right. So, usually this question helps me in understanding whether whatever I am teaching is going there or not. Okay. So, let us come back to this. Let us imagine that the sample you have has 100 particles. Okay. For simplicity, maybe let me draw like 9 particles, 16. Okay. So, when you apply very high magnetic field, so imagine each square is one particle. Okay. So, when you apply very high magnetic field, all the, okay, let me use this symbol and this symbol to represent magnetization into the TV or out of the TV. Okay. So, when you apply magnetic field in this direction at high field, all are pointing into the board. Okay. Now, you come to this point. Okay, that means the field is 0. This MR is slightly lower than MS. So, what could happen is that out of this 16, maybe one of them is now this direction. The remaining all are still the magnetization of the remaining 16, remaining 15 will be pointing into the board. Okay. Now, when you come here, M is 0. So, M is 0 means what, like 8, 8 of this is pointing in this direction, 8 of the remaining units are pointing in the opposite direction. Only then the net will be 0, right. So, by applying this coercivity, you are reversing only half of these whatever magnetic units into the other direction. Okay. So, when you apply very large magnetic field, then again all 16 will be having magnetization in this direction. Okay. So, this field is called the saturating field. Usually people use the term H s. So, H s is the field where you magnetize all the grains or whatsoever into one direction. So, in coercivity you are only switching half of the magnetization. Okay. So, coercivity is the field required to reverse half of the magnetic moments. So, out of the 16 you have only reversed 8 of them, as a result you get 0 magnetization. Okay, next question, this one we will do later, not taught yet, not taught yet. I want to find out where is this question. Okay, now we'll do this question. Any question from online?
There is one question.
Okay.
If not moments, then what are we measuring in the paramagnetic region?
If not moment, what are we measuring in the paramagnetic
Regions.
region?
That is the last session question.
Huh?
Last session question. Before break.
Before break, what was the question?
Like in the paramagnetic
Okay.
region, if you are not measuring the moment, then what we are measuring?
You are measuring the moment only, right? I don't know. Okay. Okay, point A is saturation magnetization. Almost all of you are right. I want to see like 100% correct for this kind of simple questions. Anyway, mostly correct. Next one. Okay, some of you didn't do the visualization exercise, more wrong answers. I think we are closer to lunch time. Okay. The correct answer is coercivity. Next one. Okay, most of you are right. Okay, so far we have been learning about how the magnetic materials will respond to magnetic field when we place them in VSM and measure the MH behavior. Okay. So, we learned how the ferromagnetic materials will behave. So, maybe we will briefly discuss this one, then go for lunch. Okay. So, the next question that I am going to answer is are there different types of ferromagnetic materials? Okay. Yes, I mean based on how they respond to magnetic field, we can classify the ferromagnetic materials or ferrimagnetic materials into two types. So, one is called hard magnetic material and another is called soft magnetic material. Okay, so, this is nothing to do with the mechanical hard or soft property, but this is related to how easy or how hard it is to demagnetize the material. For example, if you take a paper clip, right, you as a child you would have tried to magnetize the paper clip. So, paper clip after you magnetize for certain time, it would be attracting some other magnetic material, but after some time you will notice that the paper clip has lost its magnetic poles, it does not attract magnets anymore. Okay. On the other hand, if you go to say a shop, buy a strong permanent magnet, that permanent magnet will retain its north south polarity for many years. Okay. So, based on how the magnetic remanence is retained, we can classify the materials into two types, hard and soft. Okay. So, we are looking at two properties. Firstly, the retention of the magnetization, because that is what determines the north and south poles, the permanence of the north and south poles. Okay. So, for example, if you magnetize a paper clip, okay, after some time its remanence will be very low. After some more time it may even come back to 0, that means it has lost its magnetic north and south poles. On the other hand, the neodymium iron boron type of magnet that you buy from say some shop, they will retain the north, let us say this is the north pole, this is south pole. So, they will retain that for very long period of time. So, the retention is one thing. So, the hard magnetic materials retain this magnetization with respect to MS for long time. The second and the most important property is the field required to demagnetize or field required to change the polarity from north to south. For example, if I have a paper clip again, so this is a paper clip, initially this is north, this is south. Now, I want to apply some magnetic field and change this to south and this to north. Okay. So, the field I require to change the polarity will be very small. So, typically very few worsted is enough to change the polarity of a paper clip, because paper clip is made of a soft magnetic material. On the other hand, if I have a neodymium iron boron magnet, it is a permanent magnet. If I have to change the north pole to south, south pole to north, I need to apply very strong magnetic fields. So, typically like 10,000 or 20,000 times larger magnetic field to change the polarity of a neodymium iron boron magnet. Okay. So, the coercivity or the MS or the field needed to reach this particular point will be very large for the permanent magnets. Okay. So, these two are the important properties that distinguish between hard and soft magnetic materials. So, we cannot say that these materials do not retain magnetization and they are useless. Okay. They have their own use. Okay. So, in some many applications we do not want the magnets to retain the polarity. For example, if you are talking about transformers. So, in transformer you have like a core, then you have input coil, output coil. So, you magnetize and demagnetize the transformer core many times. Okay. And this loop is basically the energy product. So, if this loop is wider, every time you magnetize and demagnetize a transformer, you are spending lot of energy. Okay. So, in applications like transformer and electromagnets, you want a soft magnetic material which does not retain magnetization or which has like almost 0 hysteresis loop. That kind of property you need for some application. For some other application where you want to retain two states, for example, you are talking about magnetic recording or MRAM. So, you are talking about two states. So, let us say this is a 0, this is 1. So, you want two states. So, you want these two states to be like not easily changed from one to other. So, you want large energy. So, the area under hysteresis loop is a kind of energy spent to magnetize and demagnetize. So, this energy will be larger in the case of permanent magnets, and permanent magnets have their own application. So, when we are talking about recording memory or permanent magnet application, we want materials with hard magnetic properties. So, we can classify ferromagnetic materials into two types and they have their own applications. So, if you talk about the writing head used for writing information in magnetic recording, that uses soft magnetic materials.
Sir,
Yes.
in the previous slide for the hard chromatic material,
Mm-hmm.
the MS value is between low to moderate. What does that mean?
Okay. I mean, if you compare the MS value of many hard magnetic materials with soft magnetic materials, you will usually find that soft magnetic materials have a large MS. Relatively, hard magnetic materials will have a low or moderate value. Okay, I will give you some number. If you take pure iron will have like say 1007 or 2200, I don't know, somewhere here mu per cc. So, if you alloy iron with cobalt, you can, I mean, for certain composition you can go all the way to 2000 mu per cc. So, these are typical values of soft magnetic material. But if you take say neodymium iron boron or some such material, the MS will be around 800 mu per cc, something like that. So, you see that this is not that high compared to this. So, that is the meaning. So, typically the soft magnetic materials have a large MS, comparatively these materials will have low to moderate. I told you that the old speakers have black magnet. So, those are ferrimagnetic materials, they are hard magnetic material and their MS will be only around 300 mu per cc, something like that. Yeah.
What is the key parameter that dictates if it would be a hard or soft material?
What property keeps the material to be soft or hard, is it? Okay, which will come to that later. Yeah, maybe tomorrow. And after a few minutes, we will break for lunch. Then tomorrow we will discuss that. Anything else? That is the immediate next topic. Okay, so I mean the definition of hard or soft is also relative. Okay, so there is no boundary line that beyond this is soft, beyond this is hard. No, nothing like that. So we are talking about relatively hard, relatively soft kind of thing. Okay, so here I give you some number about the coercivity values, for example. So, if you take neodymium iron boron, which is a hard magnetic material, they have a coercivity of around 1.5 Tesla. If you take a piece of iron, it has a very low coercivity of 0.0001. If you take a piece of pomalloy, which is an alloy of nickel and iron, so the coercivity is even lower. Okay. So, you can see the difference in coercivity values between a soft magnetic material and a hard magnetic material. So, if you wonder what is a Tesla, okay, to give you some feeling of Tesla, I have given some numbers here. For example, you measure the magnetic field of the earth, which is sufficient enough to orient a compass in certain direction, that has a field of around this one. A neodymium iron boron magnet can generate easily between 0.1 to 0.2 Tesla. And if you have seen NMR equipment, they have like huge magnets with the superconducting magnets, they can generate 5 Tesla kind of field. Okay. I mean, to give you some idea of how strong the magnetic field can be. So, you might have heard about this incident that in one of the hospital, the attendant carried a gas cylinder inside the MRI room. So, this magnet, 5 Tesla magnet, pulled him along with the gas cylinder. Okay. So, that is the power of this kind of magnetic field. Okay, the reason for the soft and magnetic property is coming next, but we do not have time to finish that today. So, we will end here, then you can go for lunch, then we will see again tomorrow. Okay.
One question from the online part.
Okay.
From the hysteresis, how do we differentiate the ferromagnetic, ferrimagnetic and antiferromagnetic?
That is a very tricky question. It is not that easy. Okay, so, how we can, that is a tricky question, maybe I will answer tomorrow.